Today I would like to look at a quick summary on vectors, how to break them into components, why we use trigonometry and right triangle geometry, and how to take a 2D vector addition problem and determine a resultant vector. What I would like to start with is a quick summary about a vector is a quantity that it's measurable and the directionality of it matters. And so they're a diagrammatic tool drawn as arrows. Technically, the length of the arrow, when you're drawing these out in scale fashion, the length indicates the size or the quantity or the magnitude of the vector. So if I had a 20-meter long vector, like that, say, a 40-meter long vector should be double the length of that, if I was showing it that way. We're going to use this just to indicate the direction of the vector, and it has some magnitude to it, but we'll put values along the length of the vector to indicate what the size is. When you add vectors, when you add them head to tail. That's going to be really important to determine the overall position and orientation of where the vector resides on the coordinate axis or the unit circle. So if I can revisit a few things here. A one-dimensional vector is just an arrow, and it's a vector that resides entirely along one or the other axis. So a 1D vector, the way we look at it, is either going to be an x vector or a y vector. And the two I have here, I have one, I'm just saying, okay, x is negative 45 meters. So this vector, if I had to show you this one, I would show it this way, and I would just write 45 meters, and to be complete, I'd probably put a minus because I'm going the negative direction. So negative for us, in most cases, is not going to mean small number, it just means left or down. If we have a y vector at 50 meters, it's got to be in the positive direction because it's not a negative. And so this is a y vector. It only has a y component. That's an x vector. Any one-dimensional vector is going to fall on either this or this side of the axis for x, or this or this. You add them mathematically, as I did in lecture. When you get to two-dimensional vectors, and I want to use this one here. Say I have a vector, I'm just calling it v, because I'm being really, really creative today. And it's, say, a velocity of something moving at 200 meters a second. Okay, that's honking. That's like 440 miles an hour at 115 degrees. Remember that with the unit circle, 0 is here, 90's there, 180's over here, 270's here, and again 360's back over here. So 115, we know we're going to be in quadrant 2. I'm just going to show roughly where it should be. And this is the way I show it, is that's 115 measured from 0. And this has a value of 200 meters a second. The thing I want you to really focus on here is the fact that we can't say this is positive or negative. To say positive or negative, it either has to be here, 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 or here. This is in quadrant 2, which means it has a negative x component and a positive y component. So it has both x and y values. So we can't say it's one or the other. It has a combination of the two that makes up where this vector is oriented. Notice that we don't have directions anymore. You can't say positive or negative with these. That is not a circled minus sign. That is how we show angles in physics. We use, as algebra uses x for an unknown, angles are shown as theta. It's Greek, so blame them. But that's the symbol we're going to use. Looks like a Death Star with a line through it. That's like a vague reference to Star Wars, so good luck with that one. So any 2D vector is going to be something shooting off in one of these quadrants. It could be here, it could be over there. I don't like brown, but who cares? It can be over here. Those are all 2D vectors. And technically, if I measured them all from 0, this guy would be over here, and this one would be measured full swing from over here. You just have to know how to read them. But if they give you this, you're going to probably do more with it than just write it and draw it in a diagram. So what I want to do is move on and look at, well, what do we do with this stuff? That's a good question. Let's take a look. Okay, that looks good. Any vector, any vector is actually made up of two component vectors, an x vector and a y vector. They're perpendicular to one another. Well, they better be. They're an x and a y, and they form a vector triangle. So you can add an x to a y and get a 2D vector. That is always the case. If you look at the ridiculous case of, if you have a 2D vector where one of the two components is 0, you have a 1D vector. So this is a simplified case of, if you had this technically is a 2D vector that looks like this. 0, 20. You have no value in the x direction, all your values in the y direction. So this goes back to a one-dimensional because you lose one of the components. This is our 2D vector right here. Now the reason we do this is because when you add vectors, you can only mathematically add vectors if they are in the same line or along the same axis system. So we can only add x vectors to x vectors and y vectors to y vectors. We can't add 300 to, if I had another vector over here I wanted to add to it. We can't add these two together. Bad choice. Can't add these two, they're not in the same direction. They're not even close. So we can't mathematically add them. What we have to do is we have to break them down, which means we have to look at what are the components that make this up. And in terms of this vector that's 300 meters, so I walk 300 meters on a heading of 135, I'm going to end up somewhere over here. Now this means I've walked in the negative x direction a certain amount, and then I've walked in the positive y direction a certain amount. And this is just basically showing you the fact that this 300 meters isn't all in the x direction, it's not all in the y direction, it's a combination. And it also shows the fact that this can be expressed as the sum of if you walked this way and then walked perpendicular this way. That's what these two numbers are going to result from. So when you break this vector down, this 2D vector is technically the hypotenuse of a vector triangle where the legs are your components. The opposite and the adjacent. That's going to be your hypotenuse. So the goal is going to be, can we break a vector, any 2D vector down into components? And then once we do that, we look at the more complicated example of what if we have two vectors we have to add together? Then we have to get two components going. So if I can revisit how you break a 2D vector into components, we have to look back at some right triangle relations and trigonometry, with the fact that on any triangle, we have all the interior angles equal 180. This right angle here is 90, which means that once you get this angle, you know this one. Notice the angle I focused on was down here at the bottom of the vertex closest to where I'd be making my imaginary origin, my x and y axis, like that. If this is the angle I'm interested in, or this is the angle, the interior angle that forms the triangle I'm making, then this will be my side opposite to that angle, and this will be the side adjacent. So this is how O and A and H line up for this angle. To determine the components, you have to use trig, so we've got to use SOHCAHTOA. So what ends up happening is, one of the first things I ask you to do is break this into its perpendicular components, which means find the x vector and find the y vector. So let's do that right now. We have 300 meters at 135. I don't want to use 135, I want to make a triangle up. And the first thing I see is that this triangle is actually made up of, I can make the triangle this way. I always draw my triangles down to the x-axis, guys, just the way I was taught, that's the way I do it. So I'm going to have my x comp, my x component here, and my y comp over here. And the thetas are going to be right in here. Now here's the thing. You always have to have enough information to figure out what your angle is going to be inside your vector triangle. If this is 135, we know that this entire thing sweeps to 180. Okay, make sure you do this correctly. Don't just do this in your head and say it's going to be da-da-da-da-da. We know we got to get to 180. You're going to be what? It's going to be 45 degrees in here. It won't be 55. Sorry, I made a mistake on that one. Just check yourself on the math. So that's going to be a 45-degree angle. So my triangle technically has a 45 here. Well, I have a hypotenuse and I have a theta. So I can use the sine and the cosine to get those two components. So the way this is set up is this is the way the algebra and the trig will always work out on these. Let's go to blue. And I'm going to kind of do these out. Let's say the y component is going to be, it's the opposite side. So that's the sine. So I'm going to write it this way. The sine of 45 degrees, which is the sine of that angle, is the ratio of the opposite side, y, over my hypotenuse, 300, and this is meters. So notice the cross multiplication that results from this. 300 meters times the sine of 45. That's my value of y. I'm just going to call it y, not y1. So 300 times sine 45. Now this is a good place to check here. I'm getting 212.13 meters. Now, check on your Casio. You have to make sure you're in degrees mode. If you're in radians, everything's going to go sideways on you. So degrees mode whenever you're doing any trig in here, anything with angles. So the y component we have is 212.13. So I'll put that in red over here now. And just for the sake of the calculations, I'm going to also do the x component is going to the adjacent side, so it's going to be a cosine. So the cosine of 45 degrees is the ratio of k, adjacent over hypotenuse. So x over 300 meters. And you're going to see the cross multiplication happening again. So 300 meters times the cosine of 45 degrees. Now, at 45 degrees, the sine and the cosine are equal. As far as this is like having a square. The sides are equal. So you're going to get the same number here, 212.13 meters. But be very careful. This is where if you're not paying attention, it's going to bite you. 45 degrees trigonometrically reads as a positive value because the calculator thinks 45 is here. You're 45 in quadrant 2, which means this vector, the x vector, is a negative component. It's going to the left. This is a positive. So when you do the trig, it's not going to give you the minus or plus. I know by default that's a positive because that vector points up. Remember, this is the way the vector goes. You can make this the combination of two perpendiculars, but remember, wherever you start to draw the vector, you got to start there with one of your vectors, the x vector. Okay, the tail's there, the head is here. Now guess what? Head to tail. The tail of your y vector starts here and travels up. So notice the arrowheads, they flow in the same direction. And so that points up, and that's a negative. So the component of this one on the x side is a negative 212.13. So technically, to get to the same spot, you could walk directly sideways to the left, 212.13, and then straight forward or in the y direction, 212.13. It'll put you at the exact same spot.